In this lecture, I'm going to talk about the deep generative models in AI. Okay, this is introductions. The challenges of the generative model is to understand complex and unstructured inputs like computer visions, computational speech, and this is the robotic taxis and natural language processings. Okay, this is some good comments by Richard Feynman. So what he said is that what I cannot create, I do not understand. And in generative models, so what generative model? What we understand, we can create it. That's a generative model. So, for example, in computer graphics, so what is the generative models of computer graphics? So, how to generate natural image with computers. So we have some high-level computer graphics descriptions. So I want to create a cube with blue at the position at XYZ, and we can specify the size and also the cylinders. So with the colors red and the positions x dash y dash and with a certain size. So this is the way we can create cube or cylinders in computer graphics, and we just generate these from these instructions. We generate a cube with blue and the cylinder with red. And also what we can do is inference. So we can infer from these visions to these computer graphics descriptions. So many of our models have a similar structures. So using the high-level descriptions, we generate output. Also, from output, we infer high-level description of these computer graphics. And the important point of the generative models is that they are statistical. So, what we do here is we learn from data. So we do learning using the data and generate statistical generative models. So we have a bunch of the images of bedrooms here, 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 and many bedroom images. And also we know the certain prior knowledges. And this prior knowledge is always necessary. And this has, using these knowledges and data, we can generate the spectrum of the images. So we have a data, and we have a prior image, and we have a graphics here. And in this course, what we learn is how we can train, or how we proceed the learnings in statistical model, in statistical generative models. So, what is statistical generative model? A statistical model is a probability distribution functions, PX. And the data is simple. So we just put the images of bedrooms, or images of the cats, or images of the dogs. And we also need some prior knowledge that should be related to the modelings of these generative models. So, for example, we assume a Gaussian probabilistic distributions with parameters like average and sigma. And we also need loss functions or maximum likelihood to estimate the probabilities. And also we need the optimization algorithm. Thus, we need some training data, and we have modelings with these probability distributions. And using these two, we generate a certain probabilistic distributions. So, in these distributions, okay, so this is a local space. So this is a probabilistic local space, and you have a cat's image, and you have a dog image. So all images are probabilistically exist in a local space defined by Px. And if we can get such a, if we can define or generate such a space, we call generative. So what we can do here is just we learn, or we call that training. We train your AI and generate continuous probabilistic distributions and determine most probable most probable images. And we generate image using most probable one. Okay, so it is, we call it is generative because sampling from Px we can generate new images. However, the important point here is that, okay, we can generate new image. However, we do not know if this is correct.
それではまずスマートフォンのロックを解除してください。ロック画面の設定を更新すると、次回からは画面のロック。
So you can generate, okay, you can generate probability distributions of images, and you can sample most probable image from this space, and we call this generative, or we call that we generate a new image. However, we do not know if this image is correct, or the images are what we know. So this is a statistical generative models, what we are going to learn in this lecture. Okay. So anyway, this is somehow useful. So let us just think about how we can build a simulator for data generating process. So we can think about the data simulators, and using this data simulator we generate data. So this is some usually what you do. You just do the simulation and you generate a new data here. However, in data generating, building a simulator for data generating process. So what we do, what we call for generative. Tip is that you have a control signal and you have a data simulated, and then you get new data points. So this data simulator is neural networks, and you train this neural network using data. So you can generate new data points. However, the important point for generative model is that probability values and also potential data points. So you have a image space, for example, of the cats or dog, image space, or sometimes we call manifold. So you have a cats, or you have a dogs, or you have a human beings, and these are all images. And how you define this image manifold? It's you use a neural network with training data, and we call that variational. So each images have a in this space you have a probability distributions. So some images have a very high probabilities. So what we call generative is that so you have a data, you train this simulator neural network. So you have a neural network and train from using the data, train these neural networks, and to obtain the probabilities of the images in a certain local space. So there is two ways you can use these data simulators. One is to use the control signals to get new data points. This we also call generative. Also, for some data points you do not know, unknown, data points. So you have images with cats without these bears, or without mouse. So these mouse or eyes is missing, some part is missing. You give a certain missing data points to give the neural networks to get the most probable. You get the most probable images. So please just understand what you have here is you have a control signals, or you have some missing data. You can generate new data points. You can generate probability of images, and you can choose most probable one. Choose. And in generative models, what we do here is we call this is a data simulator. However, this data simulator is a statistical models. Okay. And this statistical model is the we call generative model. So what we do here is statistical learning. And what we use here is Bayesian model. And this Bayesian model is based on neural network. Okay. So what we learn is how we can generate or how we can model these neural networks, so-called generative model. And this model is probabilistic. Usually we model this using Bayesian. network. Okay. So let us talk about how we can generate data in the real world. So this is a generative model of realistic images. Okay. So what we do here is just anyway, this generative model has many models. And we have a energy model. Anyway, statistically, these are all Bayesian. Energy model and the flow model. Many of them are physical model, flow model, or diffusion model. Or sometimes you call that score function model. Or diffusion score function model, or something like that. And what we need to do is just train this neural network with data. So you need to give the data. So what type of data you need here is, for example, so you give a very rough data. Rough, maybe this is handwritten. So you may give a handwritten flat image. And you give a neural network to generate, for example, the stroke paintings or realistic images. So you can generate the from a rough image to stroke paintings or realistic images. And for example, so you can give us just text. So say Ace of Pentacles, and then you know that generative models of paintings can generate language artwork creations. Okay, so you have a like a DALL-E. Anyway, DALL-E 3 or many generative models, and you can just use this DALL-E 3 or something like that just to give a text to generate something what you want to generate. Okay. And also in generative models, what you can do is an inverse problem. So, for example, what we are going to talk about here as an example is medical image reconstructions. So what you can do here is you have a CT here, and you put CT is scanning human bodies with X-rays. And what generative model can do is these CT generative images can make a bunch of slices here. Here you have a slices here. Generate the slices here. And what you can do here is you generate, sometimes we call the super resolutions. So, for example, you have a rough images of slices, and you can generate super resoluted images to find some cancers or problems in these images. Also, what we can do here is outlier detection with generative models. So, for example, you have a traffic sign images, and you can judge if your traffic sign is okay or wrong. Okay. So, for example, you have images with a speed limit of 35 miles, and the 35 mile is, of course, this is okay size. However, sometimes, so what I mean here is, if your neural network is well trained and wise enough, you understand this image is 55% okay. However, you have such images, and with certainly damages here. So what you get here is something wrong with low probability, maybe 5%. So what generative models can give you is, if you feed a image A and image B, your generative model, that is a probabilistic model, can give you a probability of these images, validity of these images. And if you use like a chat GPT, give you a certain text, you can get the most probable. What I mean most probable is your neural network generate probabilistic space of the images, and your text or your data can specify certain point in your probabilistic space with probability of some images like this one. So 5% images like this one. Okay. So okay, probably in today's lectures I have no time to talk about GAN. GAN is generative adversarial networks. And anyway, GAN GAN is a very how to say, the first generative models proposed by the Ian Goodfellows. Okay, and you can generate certain images from the text to image. So the very first GAN generated image is 2014, 2015, 2016, 2017, and 2018, and 2025. So this is the progress of the generative images using the GAN network. Okay, and also we can generate. Okay, so after the GAN, in 2015, so-called the diffusion model is first proposed, published. And 2020 whole, and this diffusion model is purely physical model. And this physical model is based on Langevin. Dynamics. And the first paper is too difficult for people to understand. And 2020 whole, we wrote these papers with easier versions, and people understand this diffusion model is very, very useful. And this is images generated by diffusion model. Okay, so you can compare with the last images with GAN diffusion model. And the diffusion model considered to be a very useful, however, needed lots of the computations. So this means that you need a lot of the electric powers. Okay. So let us talk about text to image diffusion models. So nowadays people using Okay, so this is a text-to-image diffusion models like a DALL-E or ChatGPT. And so, for example, you can give an astronaut riding a horse. This is a famous image. So you get the astronaut with riding horses. So this is a DALL-E 2. DALL-E. I think this is DALL-E 2 image. So this is an open model, open generative models. Okay. So, for example, you can give a ChatGPT or certain ChatGPT or DALL-E. I think DALL-E is already included inside ChatGPT. So you can give a perfect Italian meal. This text to neural networks. Neural networks. The perfect Italian meal picture images here. So what you can do, what you do here is you use the Chinese to say teddy bear wearing a costume is standing in front of the hall of Supreme Harmony and signing Beijing Opera. So teddy bear 穿着西服站在大和殿前唱京剧. So if you give such an input image, so DALL-E 2 diffusion models can generate such images. Okay. So you have a minimap diorama of a cafe alone with indoor plants. So this is a DALL-E 3 text. This is a text input. Text input. So you give a text input minimap diorama of a cafe adorned with indoor plants, wooden beams crisscross above, and the cold brew station stands out with teeny bottles and glasses. So you have tiny bottles here and a mini dialogue of cafe adorned. So you have a cafe here and you have indoor plants and wooden beams crisscross above. So you have wooden beams crisscross above. And the cold brew station stands. Cold brew station stands. Okay, here you have a cold brew station stand with tiny bottles and glasses here. So you generate such an image using the generative model. Okay. So generative models also can do the inverse problem. So what inverse problem means? For example, so you have a low resolutions to high resolutions with probability. Okay, so you have a target, probability of the target, and you have a probability of original. event. So this is Bayesian statistics. So you give a low resolution data, you generate the high resolution pictures here, and also you have a masked, we call that in painting, mask in painting. So you're missing some data here. You can recover some missing data from here to here, and this is the inverse problem. So you have some raw information data to perfect or higher informations. Okay, so for example, you can just create from the grayscale to color images here. So these are all what you can do in generative models. So for example, you have a handwritten kids painting. So this is the input, and you use the generative models. So you can use the generative neural network to generate realistic image. Here. So all these are fun, and this is the progress in inverse problems. So you have an input here. So you have an input here. So what you can do here is you have a stroke painting to image. So you just input some images with handwritten images or flat paintings. Okay, and these are output. And also what you can do here is editing. So you want to put this, so you have a lake here. However, you can change this to different images. So you have these pictures. You have a lot of the clouds here. However, you can generate a more clear sky view here. So you can edit your image, or you can generate more realistic or stroke painting. Paint. Okay. So these are all the inverse problem. So what I say inverse problem is you put the lower information to higher information. You have a probability. Here. Okay, so this is the input image, and you can put a text, a bird spreading wings. So you can generate a new image with spreading wings. So you can give a box and say a photo of an open box. You can get the open box photos. And you have an input image with two bars, and you can give two bars a kissing. You can generate a kissing bird image. And you have a dog, standing dogs. However, you can give instructions, text, a photo of sitting dogs. You can generate sitting dogs. And you have input images of goat and cat. And you can say that a goat is jumping over a cat. You generate a new image here. And you have a children's drawing of waterfalls. So you have a waterfall images, and you have a children's illust. So you can generate something or edit something, some images with different styles. And these are all generated by diffusion model. Okay. So also you can do something. We can do obtain a medical image using this technique for medical image reconstructions. So what's CT? Computer tomography. If you do is you have a X-ray source. So you emit X-rays, and so you have a you have a multiple. So this. So what you do here is you have a X-ray scanning, and you have a multiple detectors. What multiple detector means that you rotate this source and detectors. So you view these human images from different directions and construct these cross sections. Cross-section of human images. So you have a sparse view xenographs with for different species, and to generate. So you have a very small number of the cross sections to generate whole cross sections using neural networks. So you have using your neural network, what you can do here is you have a less X-ray damages, because X-ray is very harmful to human bodies. So you can use a neural network to have less X-ray damages for computer tomographies. Okay. So what you can do here is forward image. So what you can do here is you have a PX and PY. So you have a raw informations or raw resolutions. data here, you get high resolution data. And this is a generative Bayesian or statistical generative model. So this is what we are doing here for generative model. So this is a wavelet. Wavelet is anyway. This is a wavelet transform. So I hope everybody knows about the wavelet transform. What is a wavelet transform?
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. The Blue Lagoon is a 1980 American
So you can do this wavelet analysis using the generative model. So you have an input and you have a neural network here, and what you can do is text to speech. So you input the text and generate the output, and you have a neural network. And this neural network, so you have a text input, so you generate the output. So you can generate a text to speech. Also, you can give it unconditional, so no input, and you can generate a certain music here. So
once you have the first token,
so you can use this wave generative model, and you can generate speech signals from the text to speech signals. So you have a text and you have a speech signals you can generate here. So this is some example.
Once you have the first token, you want to predict the second token given the input and the first token using
CS236 is the best class at Stanford.
And another example.
CS236 is the best class at Stanford.
So another example here is super resolutions. So what you can do here is you have lower resolutions of the signals, speech signals. So you have a time t in x directions, and you have a frequency. So you can just give the base frequency of your speech signals, and then generative models can generate the higher resolutions, higher frequency data. So in this generative models, this is a Bayesian model. You put the lower resolution signals, which means you have only the base frequencies, and the generative model can generate higher resolution signals. However, what I mean here is probabilities. So this is most probable higher resolutions. Okay. So also here we have a language generations. So like a ChatGPT. So we have a customer prompt. So to get an A plus in deep generative models, students have to something. So you want to get the good records in this class. So what student have to do? You can ask this in ChatGPT, and ChatGPT can give you to get an A plus in deep generative model. Student have to be willing to work with problem that are whole for most interesting than say the ones that most students work on in else or something like that. So anyway, you can ask something, you get some text to complete. Okay, so this is something. You have a previous words, and the generative model can generate next words. So to get an A plus in deep generative models, students have to the next words will be completed in this generative models. So what should I do to get A plus in CS 236 at Stanford? So you have a certainly some conditions, or some sentences can be generated here. Also, you can do the machine translations. So you put the Chinese text, you generate English text, and so anyway, this is encoding. So you encode the Chinese text, you get the decoder as English. So this is also the generative models. So you put the Chinese text and you get the English text. You get the probability of the English text. Okay. So also you can do a program code generations. Code generations. So if you are taking the basic program courses, you don't have to program. So you just give what you want to do here. So press the list of the expenses and return the list of triples, data, value, currency, and you do some very simple programs to calculate your accounting or something like that. So your ChatGPT or your generative program can generate a program for you. And this is a video generations from text to video. And the last example is text to program. So you give a text. Suddenly the walls of the embankment broke and there was a huge flood. And then you can generate such a video. Okay. And also this is a text to video generations. So you put the you put the video, you put the text, you generate video. So a couple of skiing down a snowy hill on a tire Roman cycle style or something like that. A couple sledding down a snowy hill on a tire Roman chariot style. I don't know what this means, however, anyway. So anyway, you can generate any images, whatever you like. So this is a different one. This is with the music. Okay, so pretty cool. So this is another imitation learnings. So you have a past observations. You generate a new actions. So this is a conditional generative models also. Okay. Okay, so you put the past observations, you get the new actions. Okay. Also, this year. So we can also generate molecule generations. So 2024 Nobel Prize in chemistry. Is a molecule generations using the AI. Generation using neural networks. Okay. Also, we can generate a fake image. So sometimes we call it deep fake. So you have a real image, and you can generate or edit different images from the original ones.
We're entering an era in which our enemies can make it look like anyone
very
is saying
interesting.
anything at any point in time, even if they would never say those things. So, for instance, they could have.
So this is a deep
like,
fake.
I don't know. Killmonger was right, or Ben Carson is in the sunken place, or how about this? Simply, President Trump is a total and complete Right. Ben Carson is in the sunken place. Or, how about this? Simply, President Trump is a total.
So you can let any president or any important person to speak something fake. So so this is a roadmap of this course. So in generative model, so we have a we need to think about representations. How do we model the joint distributions? So you have a P higher informations. Given lower informations or nothing to get the probability of image, text, video, or whatever you like. So what you have to do is just model this one and let your neural network to learn. And the learning is also very important. So what is the right way to compare probability distributions? So you have a bunch of data. So you have a data and you have a model families. However, is these data representations or data distributions? Can you generate a good model or not? Okay, and also the inference. So you have a model, you have a trained good neural network models. However, what you can get infer, so you get the probability of certain images. So what you can get from the lower information to higher information is the inference. How do we invert the generation process? Vision as inverse graphics or something like unsupervised learning. We cover high resolution description from raw data, or you can generate you can give a text to make a good program. So representation, how do you generate and how do you learn, or how do you train your neural network to generate the probability distributions? Also the how do you get the higher information from lower informations? These are key challenges of your generative models. Okay.